Hi, my name is Jason. I'm one of the MongoDB As at ObjectRocket. Today we're going to talk about MongoDB and scalability. A little bit about me. I started off in relational databases, primarily MySQL. Had a chance to then work with compression engines and also columnar databases. My first NoSQL project did involve Mongo, and it was regression testing for a production application. After that, I made the switch to NoSQL at ObjectRocket by Rackspace, and been doing NoSQL ever since. Today we're going to talk about these few topics that will help you scale your database and your application. There are obviously more ways to scale, but these are a good start. So traditionally, you had two types of scaling. Vertical, which is scaling up. That's more CPU, more disk, more RAM, just more resources in general. And then scaling horizontally, which is scaling out. And in MongoDB, that's sharding. One benefit you have to scaling out is linear growth for performance. Vertical scaling up cannot guarantee that. So scaling in Mongo starts with a schema. Schema design is very important to how well your application is going to scale. And we'll talk about these few topics specific to your schema. So what you see here is the same document, but two different versions of it. MongoDB will tell you you should not and don't have to use short field names with Warrior Tiger just because the field names are then compressed, but that's not true. Warrior Tiger will only compress the field names on disk and will not compress them while they're buffered in RAM or over the wire, which can be costly over time. The example that you see here would be the document on the left is 193 bytes and the document on the right is 132 bytes, so that's a savings of 61 bytes. That's not a lot of bytes on a few thousand documents, but when you're talking about 1 billion documents, that's roughly 56 gigabytes, and that doesn't include the padding factor when you're talking about storage. So that's a savings of 56 gigs that you had to page in and out of RAM and over the wire. Smaller documents, like I said, require less RAM per document and can give you a measurable difference in performance. Another point was type. On the left, you can see where the date was stored as a string, and on the right, stored as an ISO date. That alone will save you 16 bytes there, which over time, again, will add up. Next, you see, next we can talk about arrays. In this example, for space, I only have one element in an array, but arrays in MongoDB are common, and it's common to see hundreds or thousands of values in here. Just be cautious with them. They can impact performance in a couple of different ways. One, if you start filling up that array with thousands or tens of thousands of values, you may approach maximum document size depending on your elements, and that's not going to scale that well. Also, if you decide to index these arrays, every element in that array will be a pointer in the index. So that means if you have a document move and the document is moved on disk, it's going to have to update the pointer for every element in that array, which can be costly on writes. Another good use case is embedded documents. Not shown here, but just embedding more information in the subdocument, which is one benefit of using MongoDB in the JSON document format. Just be cautious when you're retrieving that data. You really want to use projections. Projections allow you to limit the data that you're pulling back from the database and will allow your reads to scale a lot more efficiently and decrease the network traffic between the MongoD and the MongoS, or the MongoD and the client. MongoDB has a few scaling options, not just up and out. We will talk about these next. So the first one, as mentioned earlier, is vertical. Vertical, again, is just adding more disk, more RAM, more CPU. This, from an application perspective, this particular scenario from an application perspective just requires read consistency. You may not be able to shard at this time, or sharding hasn't been a requirement at this point in time. What you have here is increased hardware costs and possibly costs associated with upgrade cycles. This form does reduce complexity. You don't have to worry about the config servers, you don't have to worry about the MongoOS tier. You can connect directly to the replica set to get your data. But it can cause scaling issues for when you need to perform things like maintenance tasks. If you have to build a large index, or if you have to take out a node for an initial sync, that degraded window is increased in this type of vertical scaling, just because an index on a 200 gigabyte collection is going to take a lot longer than it would be if you were scaled out. Next is using replica sets. So your pros and cons are very similar to vertical scaling. But one benefit you have here is your application, if it allows for eventual consistency, can utilize the other nodes in the replica set for the read operations. In this case, you could say one secondary is for reporting, or one secondary is in a different geographical location, and you can hit that secondary to have less latency for those particular reads. You do want to be mindful of your workload and make sure your workload works properly with secondary reads. If part of your workload doesn't, you could set your read preference for some of your workload to only hit the primary, and the rest of your workload to hit a secondary. And for Mongo, the most reliable and most robust method of scaling is sharding. And this is horizontal. This does increase complexity because you have a MongoOS tier, you have a config tier that you also need to manage. Then you also have a lot more members and nodes to keep track of and make sure they're running optimally. But what this does allow you to do is it allows you to grow linearly and increase your array scopes. Every new shard that you add will increase the number of the amount of throughput you can handle. And like I said, as you need more throughput, you just keep adding shards. This can simplify maintenance. As I mentioned before, the collections per shard, or the collection on a shard is a lot smaller than it would be on a vertically scaled collection. And the maintenance will be quicker and can be done in parallel. For example, if you had to add the index, you can add the index to one tier of the secondaries all at once. It's going to be very fast because it's just a subset of that collection. You put that secondary back, you do the operation on the other secondary, and so on. To help manage the increased complexity, definitely recommend aggregating your metrics and your logs because, for example, if this cluster was larger, you'd have to possibly connect to 60, 90 nodes to collect information, and that could be time consuming. So definitely have metrics and log aggregation in place. Another way of scaling in Mongo, which some of the presenters have already talked about, is the pluggable engine API. For a while, memory map was your only choice, but now you do have RocksDB and WireTiger, which have been previously talked about. An example would be that you an example for, say, vertical scaling would be you need more write throughput, but you don't want to shard just yet. You could then consider one of these other engines for higher write throughput, assuming your workload works very well assuming the engine works well with your workload. An example is the memory map storage engine does really well at in-place updates, where WireTiger does not do well, and that's because memory map has built-in padding, which is a power of 2, so that means your in-place update may not require the document to be rewritten, which saves on disk I/O and saves on performance. WireTiger, on the other hand, will need to rewrite that document every time, no matter if you're just incrementing a single integer or adding an entire string. RocksDB was previously talked about. That's an LSM-based engine. A good example, a good workload for, say, RocksDB is chat or messaging app where your most recent data is at the head of the LSM tree, and you're writing and reading to the head of that tree. So when scaling Mongo, locking is typically why you need to scale it. And here we'll discuss some of the locking granularity over the last couple of years with MongoDB and how the Mongo version and engine will influence that locking. Version 2.4 and 2.6 is the database. These are the defaults, by the way. And 3.0 collection level, and then in 3.2 the document. And the engines on the right dictate what type of granularity those versions add for locking. One way to work around that locking is by separating your data into other databases and or collections. And the reason I'm talking about drops here is a common use case is you have data that you want to remove, but a TTL may be too expensive. The removes by the TTL may be too expensive and will impact your application. In this case, you can pre-shard and pre-split collections have multiple collections or even into multiple databases. And when you don't need that data any longer, you could then drop that collection, which is a very quick and practically free operation, or at a low time, drop the entire database from your replica set or sharded cluster, or from your replica set or sharded cluster. The database drop is not free, but it is a momentary global lock while the data files are being removed. I mentioned previously about TTLs and how the added deletes could impact your workload. A couple recommendations there. Do not just apply a TTL and expect it to throttle its deletes. If you apply a TTL, it's just going to start deleting whatever it can as fast as it can. The recommendation there would be to add a TTL with a high value and then gradually step that value down, so you're slowly removing documents that are beyond the desired value. The other recommendation there would be having an offset. For example, if your peak traffic is at noon on a business day, don't have the peak TTL deletes also be firing at noon as well. Offset that by, say, 12 hours, so your deletes are happening at night while your inserts and updates are happening during business hours. It usually doesn't impact you, but secondaries do have different locking when it comes to the memory mapped engine and also WireTiger. The replication thread will actually grab operations in batches and apply them in parallel on the secondaries, so the locking there is in serial like it is on your primary workload. So now we'll talk about sharding. We'll discuss some of the components of sharding and how you will want to adjust your workload so that you can fully utilize the benefits of sharding. So the first tier, the MongoS tier, which is responsible for the query routing and connection handling. This is the tier that your clients are going to connect to. The first example on the left is putting the MongoS on the application server. This is a common use case, but has one problem. If that MongoS goes down, you've essentially lost that application server. You could have a list of MongoS's depending on your driver version, but then you have to curate that list in case one of them is lost or you're scaling up and down. There could be some overhead there that you don't want to worry about. Workaround for that is using some type of monitoring on that host just to make sure that process is always running, and if it fails, stops, or something happens, just restart it. The next option is putting a load balancer in between the MongoS and the application. This is very common, especially with older drivers that did not support MongoS load balancing the MongoS servers at the driver layer. In this case, if you wanted to use a HA proxy, you just put a HA proxy layer in between your application and your MongoS servers. Just make sure that that your hosts are being hashed correctly to the like I think you call it the source hashing, so that the connection sticks to the same Mongo OS. You don't want the client connection coming in, opening a cursor, and then when it comes in to get its next batch, be sent to a Mongo OS. You're going to start seeing errors where cursors are not found, and your application is going to, those errors are going to bubble up to your application and your end user. You want to make sure the client's going back and getting the cursor from the same Mongo OS. And lastly, the new drivers, most of the new drivers support load balancing the Mongo OS at the driver layer. So this handles, this removes the single point of, that removes the extra point of failure of the load balancer and the possible bottleneck caused by the load balancer. Your driver now is responsible for the health checks and connecting directly to the Mongo OS. One word caution here is you will see increased connection counts from your application servers. With the load balancer, you have just one endpoint, and the driver only has to check that endpoint. In the last option there, each Mongo OS is going to, each application server is going to connect to each Mongo OS and have health checks and latency checks to see which Mongo OS is healthy and which ones it can use. I would consider Sharkey Selection one of the most critical parts of sharding. This will determine your throughput and how your application will interact with the database. Shard keys do have limitations. When you decide to deploy sharding, some operations are no longer allowed to be run on collections or databases, and you want to be mindful of the operations that you are running, because as you see, shard keys are immutable. So that means if you had two documents and you needed to merge those documents, you may have to pull that back from the database into your application, remove the document or documents from the database, and then put that back depending on if that fits your workload scenario, if that fits your use case. You can't, if your shard key is on a user ID and you need to update that user ID, it's not going to let you, it's going to error. Shard key selection is also going to determine your throughput. You want randomness here. You want to distribute your writes among all shards to get maximum throughput, and not have some shards handling a majority of the writes. With that, you also want your reads to be targeted, and your update statements to be targeted. You don't want to be broadcasting them to all shards in a replica set, wasting CPU and resources on those. And also be mindful of merging of data. For example, if you do have a scatter gather that's broadcasted to all the shards, with or without a projection, the Mongo OS is now going to have to merge that data back together for you, sort it, and then return it back to the client, which can be costly for the Mongo OS and sometimes put added work there. Also with aggregations, and I believe in 2.6, when merge cursor was introduced, an aggregation that has to contact multiple shards for that data will actually reach out to the shards at the MongoDB layer, run its aggregation, bring that data back to the primary shard, and then hand that back to the Mongo OS. So that's one thing to be mindful if you're running a lot of aggregations, that one primary shard might be overloaded. I believe in future versions, if not 3.0, 3.2, I think they randomized that so the merge cursor operation would actually execute on not the same shard all the time. Next is chunks. This is the logical distribution of your data. Here you want high cardinality to prevent jumbo chunks. Jumbo chunks are chunks that either exceed 250K documents or the chunk size set in your settings. The reason this doesn't scale well is because you may end up with chunks or data that can't be moved off of a shard, and if you can't move data, that could be a problem depending on your environment. Highly recommend pre-splitting collections. You could either create collections or databases in advance and pre-split, or if you don't need to, if your workload isn't that where you have to drop and recreate databases or collections, pre-splitting collections on a new deploy will improve performance and throughput from the start. This can be done with num initial chunks on hash shard keys, or by pre-splitting your chunks ahead of time for non-hash shard keys. And then keep in mind the balancer overhead. At the lowest layer, the balancer is nothing but inserts and deletes. So on the donor shard, on the source shard, you're going to have inserts. On the donor shard, you're going to have the deletes. Be mindful of this. This can impact your application and your workload. If you do have to balance, I would recommend setting a balancer window so that these operations are during your off hours and not impactful to your application. And lastly, the Sharkey Selection process. I would recommend a tool like Variety to analyze your schema, just to make sure you know what fields could be potential candidates or what fields could immediately be ruled out as a shard key. For example, a shard key must exist on every document, which Variety will tell you if you decide to scan your entire collection or a portion of it. Next, enable the system profiler and capture all operations. Increase the size of the system profiler so you get a good window of operations. This will tell you what operations are most frequent. This will tell you what patterns are most frequent. And it can also tell you if you're violating any of the unique constraints any of the constraints for a shard key. And then last, test this in a staging environment and QA it. Don't go right to production with this because if there's a use case you didn't find in the profiling, you may break operations, writes could stop happening, and you'd have to unshard that collection, which will result in some type of downtime, depending on how large the collection is. So here's an example of non-distributed writes, where I was talking about before that the shard key was sequentially increasing. So you can see the chunks that had the most recent values were on the shards to the right, and they're going to be receiving most of your read and write operations, and they're also going to have more data than your other shards until that data has a chance to balance. And whether you're running the balancer 24/7 or during a window, these move chunk operations are going to be ongoing to try to balance the data out to those other shards. This is not an efficient use of all your resources. The solution to that is hashing that shard key. In this case, the randomness of the hash value will spread these writes and reads out to multiple shards. And as long as you include your shard key in your operations, your reads will also be targeted to those shards as well. This is a much more efficient use of your resources and all of your write scopes. Here's an example of a targeted operation, which I previously mentioned. Again, this is efficient use of your resources. The collection here is sharded on U and C_at, and those values are provided in your find criteria. In that case, the MongoOS will route that query to the shard containing the chunk for that range. Here's an example of a partially targeted operation. This is not as ideal as the previous operation, but it's still better than broadcasting these operations to all shards. In this case, because the key is prefixed with user and user was included in your query, the MongoOS was able to identify what shards it needed to send the operation to and query those shards. And then here's an example of the scatter gathers or the broadcast operations. This is on a field that is not part of the shard key because the shard key is not, at least the prefix is not in the query. MongoDB has no choice but to send that operation to all shards. This can be very costly. An example here would be if you had a limit on this operation, that limit is actually pushed down to the MongoDB layer, and using the limit of 50, each MongoDB, if it has at least 50 documents, is going to have to return those 50 documents to the MongoOS, and the MongoOS is then going to have to sort and merge that data back together to be handed back to the client with a limit of 50. So in this case, you are transferring and retrieving a lot more data than you really need to. We have seen use cases where this is actually putting a lot of stress at the Mongo S layer, especially if you're not using projections and your documents are relatively large. And this was touched on earlier by I think Kim and Peter, I believe. Use the right tool for the job. Mongo is really good at unstructured data. For example, retail catalog data, social media data, analytic data roll-ups and gaming profiles. Stuff that you want to, that doesn't necessarily have a structure, and you want to add or not add certain fields to certain documents. Mongo may not be the right tool for the job for some of these. It can do these, and in some use cases it can do them really well, but in other use cases you may have difficulty scaling some of them, and that includes text search, where you may want to look at a tool like Elasticsearch, Geo, again Elasticsearch, Postgres, key value stores. Redis is a good example, or if you need transactions, and RDBMS may be the type of database you want to use. Questions? Sure.
Well, you're talking about hashing your Sharkey.
Yep.
So you say your username was an email address, and you hash that and made a separate index which you use as your Sharkey. That then, I'm just making sure that I'm thinking about it right? Because that's a static, really final value. It's never going to change that hash. So even if the user comes to the backend and gets your email address, you're okay with it. Said if you use that email address, it would be immutable from that point on as a Sharkey. Is that right? I said that earlier.
Yeah.
After you hash it, so after you hash the value, then that just stays static. And that's what you use.
Well, immutable, you wouldn't be able to change. You wouldn't be able to change that value. You can still insert other documents with that same value, and they would just belong to that chunk with that.
All right.
If you needed unique constraints, that's a different consideration. But it would it would take that email address and it would hash it to, what it does is it runs an MD5 on it, and then it takes the first 64 bits of that MD5 and then converts that to a number long, and that's that hash value that you would see in your chunk table that says this range of hashed values belongs here.
And in that use case, you would probably want to hash the underscore ID so that you can change any of that user's attributes, and it would be regardless of that actual underscore ID.
Yeah.
Okay.
And that helps protect that flexibility without hampering.
But if 90% of your operations are on that email address, and you're not going to have to worry about a jumbo chunk, that would give you the targeted reads and targeted updates.
Thank you.
You're welcome. Thank you.